Okay, so today we start with the linear transformations. This is chapter 4 of Artin. So essentially, the idea is that we are considering transformations from one vector space to another, which are analogous to something known as the homomorphisms of groups. Essentially, homomorphism is a map that preserves the structure, the group structure, the structure for the vector space, if it's a mapping from one vector space to other, so on and so forth. Uh, so this is a map from one vector space over a field to another. So why we say it preserves structure? Essentially, whether you apply a map on adding the first vectors in V, so V1 and V2 are in V, or you apply a map individually and add them, and also similarly scalar multiplication is compatible. It is compatible with the scalar multiplication. So these maps are called as linear transformations. And we can show by the above that, of course, by induction, this ought to be true. So what is the most immediate example that comes to your mind? Some transformation that takes vectors from a vector space to another vector space. What sort of an example comes to your mind? Well, it is the left multiplication by a matrix A. So I multiply a matrix. Let's say I have a M cross N matrix, and I multiply it by a column vector. I get another column vector. So these are column vector. This is a column vector. So this goes to by left multiplication by A. So x goes to ace of x. Of course, you can certainly verify that this is true for matrix multiplications, and this is also most certainly true. So what are the other examples we can think of? Well, consider the vector space of real polynomial functions of a degree less than n. So, real polynomial functions of degree less than n. So I have and then the derivative is a linear transformation. We'll just call it LT from the space Pn, n degree polynomials to Pn minus 1. So let there be a linear transformation taking vectors from V to W. There are we introduce two subspaces. So one subspace belongs to the vector space W and the other belongs to V. So let's define the kernel of the linear transformation. It's called the kernel of T. Is a vector space such that the elements are such that these guys are 0. And the image of T, known as the image of T, is a vector space, a subspace of W. So T is the subspace of V. Image of T, kernel of T is a subspace of V, the vector space, and image of T is a subspace of the vector space W. So this is such that for some V element of V. So this is the set of image of T consists of a subspace of W such that each of these W has a pre-image V in this vector space. So that's basically the idea. So kernel of T is a subspace of V and image of T is a subspace of W. So it is convenient to interpret them as a left multiplication by a matrix. So consider the matrix A. Let's say my linear transformation was the multiplication by the matrix A. So the kernel of T is nothing but Ax equals to 0, set of all x such that Ax is equals to 0, this condition. So that gives me the kernel. And image of T is a set of vectors. So this defines the kernel of T. And image of T is the set of vectors image of T is a set of vectors such that, let's say B such that the linear equation Ax equals to B has a solution. So that's the idea of these two subspaces. And so what is our theorem? Essentially the main part of this section, which is to say that let T be a linear transformation taking vectors from V to W, and we'll just assume V is finite dimensional. Then the dimension of the vector space is the dimension of the kernel of T, which was a subspace, remember, uh, of the original vector space V, and the dimension of the image of T, which was the subspace of W. So the dimension of the image of T is usually known as the rank. This is R, the number, and this guy is known as the kernel or the nullity. And one can represent it by K. So essentially, dimension of the vector space V is nothing but rank plus nullity. Okay, so a bit about the rank and nullity. Essentially, one can also regard it as a, let's say we are considering an example of a M cross N matrix A, and I have the rank as R and the nullity by K. What is K actually? K essentially is the dimension. K or nullity is the dimension of the space of solutions of the equation Ax equals to 0. The vectors B another set of vectors B such that Ax equals to B has a solution form the image. Remember, B are the guys in W image, and that is it essentially. The sum of these two uh, is the dimension of the vector space. So that is there is to this thing. So for example, what happens? Consider the matrix A and Ax equals to 0, or we are considering the equation Ax equals to B, either the homogeneous or otherwise. So what happens in the scenario when A is an invertible matrix? So that means determinant of A is not equals to 0. So when the determinant of A is not equals to 0, we know that Ax equals to B has a solution for all B. So in that case, so of course, since we are dealing with determinants and all, let's consider this the case to be the case for n by n square matrices. So Ax equals to B has a solution for all B. That means that B has a dimensionality of n. And so what does that mean? The rank is equals to n and the kernel is equals to 0. However, when the determinant of A is equals to 0, well then there does exist k greater than 0. This is not an invertible matrix, so essentially you will have some of the guys over here which will have, so Ax equals to 0 has non-trivial solutions when the determinant of A is equals to 0. In other words, the quantity k will be greater than 0 and the rank would be less than n. It means that the image is not the whole space Fn. Okay, so how does one go about proving this theorem? So we ought to prove, I'm just going to sketch it, and I would encourage you to come up with your own arguments. Dimension of V is dimension of the kernel of the linear transformation plus the dimension of the image of V. So how does one go about proving that thing? Well, there are several ways to show it. So remember, we are dealing with these subspaces. So one can consider the subspace, the kernel of T as a subspace, and let U1, U2, some UK be the basis for the subspace. Now, either you can assume this is another subspace of W, so you can treat these guys as some V1, V2, VR as the basis vectors. So these are the basis vectors for the subspace kernel of T, and these are the basis vectors for the image of T. So that essentially is what we have. Or let me call this through a better symbol probably. I think it will be beneficial if I call them as, what should I use? Yeah, so let me use W1, W2, since this is a subspace of W. Remember, we were dealing with V goes to W, so this was the subspace of the space W. So let's say these are the basis vectors for R. So now we have to prove that U1, U2, UK, W1, W2, WR, these guys we have, so we have to prove that K plus R is equals to N, the dimensionality. So what we can do is, there are several ways to do it, but essentially the idea is that each of this W1, for each of this W1, I can, what I can do is that I can start, let's say, I can start a basis. Uh, I can sketch a basis for these guys. I can extend the basis of the vector space V to some n minus k other set of vectors, and I'll define some wi to be the image of these sort of vectors. So now what do I need to say? I need to do, I need to prove that these wi's, w1, w2, w some n minus k, this is a set S, is a basis for the image of T. Well, then it will follow that the image of T has the dimension n minus k, and I already had the dimension of the kernel to be k, so that's going to prove my result. So there are several ways to do this kind of a proof. So how do I prove that something is a basis? So something is a basis. So this guy is a basis. I need to prove that it spans the vector space image of T, and that the set of W1, W2, these guys are linearly independent. Vectors. So that is the way you can do it. How are you going to show that these guys span the space? Well, you can write any vector v in terms of the basis, this basis. So I'll write v as some a1 u1 ak uk plus b1 w1 bn minus k wn minus k, and sorry, v, I'm using this v1 vn minus k. So now if I hit it with a transformation, I have these guys go to 0. Remember, this was a kernel, and I have b1 w1 plus b2 w2 bn minus k wn minus k. So what do we have? I have some vector w which was obtained by hitting the transformation, and this vector can be represented as a linear combination of all the w's. So therefore any vector w is in the span of S. Remember, S was the set of all these vectors. So we have it. So S spans T, image of T. Now we can similarly show that the S is a linearly independent set. Therefore, S spans the image. S is a linearly independent set. We are done. We'll be able to show that S essentially will have a dimension of n minus k, and that would actually complete our proof. So how do you show that the set S is linearly independent? Well, we just write our result for these guys. So the condition for linear independence is that given this to be true, the only way to satisfy is that C1 equals to C2 equals to all these coefficients have to be identically zero. That's easy. I mean, what you can do is that you can start by writing, consider a vector V, which is C1 V1 plus C2 V2 Cn minus k V n minus k. These were the vectors of my original vector space when I was trying to form a basis. And what do I do with it? When I hit it with the transformation, I have TV equals to C1 W1 plus C2 W2 Cn minus k Wn minus k. These guys, and this is equals to 0. So what do we have? So this, what does it mean? TV is equals to 0. We started with this condition. So that means TV, V is an element of kernel of T. Remember, that was the definition of the kernel. So if V belongs to the kernel of T, we can write V as a combination of the basis vectors we use for the kernel. So this represented the kernel, remember? So once we have the basis vectors for the kernel, I'll just express V as some A1 U1 plus A2 U2 AK UK. Now notice a thing, I have minus A1 U1 minus A2 U2 minus AK UK, which was essentially nothing but minus V, plus C1 V1 plus C2 V2, the original way I defined V, Cn minus k Vn minus k equals to 0. But notice that these guys were a basis. So if these guys were a basis, so what do I have? I have all of these guys to be 0. Remember, this was a basis, and I have a linear combination of the bases to be 0. This means all these guys, A1, A2, AK, C1, C2, Cn minus k equals to 0. So therefore, it was essentially a trivial relation. This can be only true when these guys are actually 0. So what does it mean? That these guys were 0. That means that I have shown that this statement can only be 0 when all these guys are actually 0, and hence S is a linearly independent set. So what I've shown? I've shown S is linearly independent. S spans the image. So I started with the dimension of S to be n minus k. I've shown that this indeed is a basis for image of T. Hence, the dimension of the image of T is n minus k. I started with the dimension of the kernel to be of dimension k. So the dimension of the image and dimension of the kernel is indeed n. So this is the dimensional formula. You can do this proof various ways. So remember we started with, so these were actually, we were extending this to v1, v2, vr. You can, let's think, what are the other ways you can sort of prove this thing? That dimension of v is nothing but the dimension of the kernel of t plus the dimension of the image of t. We can start some sort of a proof strategy where you have u, k, these guys form a subspace. What I can do is that I can start with the, so this guy was the subspace of w. So I can start with some vectors w1, w2 as the basis vectors of these guys. W, maybe, I don't know, r. Now I can argue that what happens, I mean, what I can do is that I can write down inversely tv1, define it such that this is w1, t w2, v2 is w2, so on and so forth. So now I have to argue that I actually can get a basis. So what I need to argue? I need to argue r plus k is equals to n. So try to work it this way of not assuming the dimension to be n minus k, but some r, and then argue that r has to be n minus k. So for that, again, what do you need to do? Yeah, so just think about it. It should be possible. I have just sketched the proof which was already given in the book. Uh, but I'm sure there are other ways to show this, and we'll be doing other examples to this sort of a thing. So think about it. Okay.